So good evening, everyone. It is 6 p.m. on the East Coast, and hearty welcome to all of you wherever you might happen to be. You are in for a treat tonight. We have Peter Olinto with us, who's going to be giving you all sorts of wonderful wisdom about quantitative methods, particularly with respect to the power of regression. So if you've attended our webinars before, you know that Pete is just a fountain of information, and we really want to make sure that we do everything that we can do at UWorld to help you pass this exam. And so you taking the step to be here and giving up a little bit of your Wednesday evening is certainly a step in the right direction. So without further ado, I'm going to turn it over to you, Pete.
Thank you so much, Sam. What's happening, everybody? Great to be with you. So you've heard of Jack of all trades. I'm his cousin Pete. Check it out. So I'm a professional test taker. So yes, I passed these exams and all of them on the first attempt. But you know what's great about that? And Sam will attest to this. If we had a two-tailed distribution of the IQs on this call, guess where my IQ is? It's in the left tail. So you don't need to be all that bright. Isn't that right, Sam? To be a CFA charter holder, isn't that right?
Well, it helps, but studying is a big piece of this.
That's right. My work ethic, our work ethic, my work ethic is in the right tail, folks. So the difference between success and failure is the time and effort you put in. As a professional test taker, what I can tell you is if you want to succeed, you will start with making a realistic plan. And the CFA Institute is not kidding with the 300+ hours, as you all know. Everyone has strengths and weaknesses. So obviously levels 1, 2, and 3, but I'll just focus in on levels 1 and 2. There's just a couple of topics, and there's no way you could have possibly majored in every one of these topics. So we got ethics, quant, financial statement analysis, which is really intermediate 1, intermediate 2, advanced accounting, US GAAP, and IFRS. We got corporate finance, we got equity, we got fixed income, we got forward futures option swaps, we got portfolio management, we got alternative investments. Are you kidding me? So slow and steady wins the race. All kidding aside, if you spread this out over a reasonable period of time, the goal at level 1 is not to barely pass, it's to master that level 1 content, because Sam likes to tell me level 2 is just like level 1 on steroids. So he said, if I got on steroids, I would look a little bit like Sam, okay? So we want to do really well and have a good foundation. Like, for example, a lot of the accounting, equity, debt, portfolio management, quant, regression that's introduced in level 1, you'll see again in level 2, but in greater detail. Level 1, mostly the basic fundamentals, what we'll do tonight, simple regression. But level 2 is where we get into multiple regression, time series. So the goal is to master this information. Now, if you say to me, Pete, I can only give you 10 hours a week. Okay, give me 3 hours Saturday, 3 hours Sunday, give me 4 hours during the week. So you're gonna give me 10 hours a week. You're gonna give me 4 hours a month. Doing the math, you're gonna need about 8 months to properly prepare for each level of this exam. Now, some people are gonna be 50 hours less. Some people are gonna be 50 hours more. Obviously, if you tell me you can give me 20 hours a week, then you're at 4 months. But realistically, given your work schedule, your personal life, all that kind of good stuff, how are you gonna find the time to properly prepare? And folks, you got to build in cumulative reviews along the way. The second half of the curriculum, the good news is a properly prepared candidate sees the overlap between the content. Like, for example, everything you pretty much learn in quant, we're going to somehow use an asset valuation or portfolio management. Okay, when you see how the dots connect, all of a sudden this mountain of information becomes more manageable. Like when you understand accounting, okay, basic fundamentals, you're looking at everything from the perspective of the issuer, the borrower, the issuer of the stock. But when we get to debt and equity, man, we're going to be looking at a lot of those same concepts, but from the flip side of the coin, from the investor, the supplier of the capital. And the investor's required rate of return is going to dictate to the issuer their cost of capital. And there's your corporate finance, kind of the link between the accounting, the debt, and the equity. In between, you got that corporate finance. So what we do in the course is set the stage for, look, we're introducing this concept here in the first half of the curriculum, but this is where you're going to see it in the second half. Now, the CFA Institute authors are amazing. I mean, they have forgotten more about this stuff than I could ever hope to learn. But one of the things they don't do is really connect those dots. They don't collaborate the authors, you know, so to speak. Like the Quant author is not saying, hey, by the way, what you see in this reading, you know, is going to be applied in the reading in debt or equity or portfolio management. We will do a lot of that so you can better see why you're learning this information, okay? Like even the economics. Why do we want to learn the macro, micro, global economics? Well, we need to understand if we're looking to forecast the performance of a company, top-down approach, well, the economy is going to dictate the market, the industry, the firm, so it helps to have a good understanding. So we will do that for you. But cumulative reviews, folks, a third of the way through this curriculum, you got to stop before you take a step forward, do a cumulative review by working questions randomly selected from prior topics. 2/3 of the way through, you'll repeat that process. And then obviously at the end, you'll do your final review. Your last month needs to be strictly review mode. You're not learning anything new. Okay, in that last month, folks, you got to be strictly in review mode, doing practice exam, practicing and applying the information. And look, it's also a mental marathon. I mean, what is it these days? How many hours you're sitting down for between signing in and sitting down? You're talking 5 hours, the whole process, soup to nuts. You know, it's a mental marathon. You can't get anything wrong exam day because you're mentally fatigued. So I would love for you to tell me, Pete, Saturdays and Sundays, I could give you 4 hours on Saturday, 4.5 hours on Saturday, 4.5 hours on Sunday. But you've got to build up that mental endurance. You can and you will do it, but you got to make it happen. You got to want it that bad. Okay, so we are happy you are here. So this I'm going to show again on the back end, not right now though, because you're going to hang with me. Well, I just want to say this is going to be recorded. So anything that I covered tonight you want to see again, you've got it. We'll send it to you. We appreciate you viewing this lecture, whether you're doing it live or on demand. We have clients all over the world. So happy to provide you this discount code. While this is a free event monetarily, we recognize it's certainly not free in terms of your time, whether you're watching it live on demand. And so we want to say thank you for giving us this opportunity to show you who and what we are, how we go about teaching these concepts, okay? Because passing or not passing this exam can change the trajectory of not only your professional life, but your personal life. Because obviously the happier you are at work, the more money you're making, the better you're going to do. The happier the nicer the person you'll be to date or marry or whatever the case may be. So it's a win-win situation. With that being said, by the way, you should educate your husband, wife, boyfriend, girlfriend. Give them a regression model. What's your probability of passing? What should that be regressed against? You could put it against time and effort, but that would be boring. Let's regress it against happiness. So that regression model, well, that's inversely related. Your probability of passing, if you're very happy, you're not studying enough. If you're miserable and you're studying a lot, your probability of passing goes way up. As we've already discussed, it's not an IQ test, all righty? So it's like learning a foreign language. I don't care how smart you are, you're not gonna know the rule according to IFRS or US GAAP unless you study, all right? So just as an FYI. So you better tell your husband, wife, boyfriend, girlfriend, whoever your significant other is, they need to support you in this endeavor. They better not be giving you a hard time, because if they are, get rid of them now. That's not your soulmate. You wanna see if the person you're dating is your soulmate? I want you to talk to them about what we covered tonight. I want you to talk to them about some of the squares of the regression, some of the squares of the errors, the total sum of the squares, how you find R squared, how you find your correlation coefficient, how you're gonna find your y-intercept, your slope. If they're still there at the end of that discussion, you found your soulmate. Either that or they need mental help. I don't know. But this is not the time, if you don't have a significant other, to go find one. Tinder will only hinder your performance. And I know you're like, shut up, stupid, start teaching. So here we go. Step number 1, the key formulas for regression. A lot of this has been covered in other chapters in Quant, but if you want to do well in a regression, you got to understand your correlation coefficient. Your covariance divided by your standard deviation of X times your standard deviation for Y. We know our correlation coefficient has that range between -1 and +1. Folks, we want the correlation between the dependent and the independent variable to be high, whether they're perfectly positively correlated or negatively. We need a correlation. We don't want it to be uncorrelated. The errors we want uncorrelated. We'll talk about that a little bit in level 1, a lot more in level 2, but the correlation between X and Y, okay? So you got your correlation coefficient, you got your R squared, you're changing your dependent variable, explained. Do not use the word caused. Dependent variable, explained by the change in your independent variable. Alrighty, folks, we got our slope coefficient, B subscript 1, change in the dependent variable, given the change in the independent variable, or covariance divided by the variance of your independent variable, your slope. Alrighty, so you got to keep it all straight. Regression coefficient, coefficient of determination, your slope coefficient, etc. Alrighty, now, our goal is after we've, gone through the basics here, we're going to do an application, okay? We're going to do some problems to see, hey, do we really understand this? But let me walk you through it step by step. So linear, we're doing simple linear regression here, okay? We're going to have one independent variable. Folks, in level 2, we'll be using the letter K to symbolize the number of independent variables. So I'm going to start introducing that here in level 1 so you're very used to it. All right, so change in the dependent variable given the change in the independent variable. All right, so we want to know that variation of Y. Y is going to be our dependent variable, okay, folks? X is obviously our independent variable. What are our symbols here? Here's the actual historical value for Y, the actual historical value for Y. This is the expected value for Y, okay? That's your average value. Your sample mean for Y, your sample mean. Okay, so we're going to want the sum of the squares of the errors. This is your numerator. That formula is your numerator if you want to calculate the variance of Y. You take the sum of the squares of those errors, you divide it by your sample size minus 1. Okay, so you need to recognize, hey, that's my numerator when I calculate my variance for Y. Okay, X, my independent variable. Here's the sum of the squares of the errors for X. So there's your numerator. Why am I screaming at you guys? Because I am very excited. There's my numerator for the variance of X. So sum of the squares of the errors for Y, sum of the squares of the errors for X, n minus 1, there's our variance. Why is that so important? Because I'm going to want to take the square root of the variance for X, the square root of the variance for Y, divide that into my covariance. Now, how do we calculate covariance? Well, if you're given your correlation coefficient, you multiply that by your standard deviation of X times standard deviation of Y. Or, if you got to do it longhand, what's our formula for covariance? The sum of the errors of X, actual X, what we thought X was going to be, the errors for X, times the errors for Y. All righty. So over that time period, you don't square anything. It's the sum of the product of the errors of X times the errors of Y over whatever time period you looked at, 10 years, 20 years, 30 months, 60 months. You have to go every year. Here's what I thought X was going to be. Here's what it actually was. There's the error for X. In that same year, here's what I thought Y was going to be. Here's what it actually was. You're going to multiply those errors together, sum it, that becomes your numerator, and then you'll divide by n minus 1. Do not square anything with covariance. Okay, now, symbols, you ready? Y with nothing above it, that's your actual historical value for Y. So we might be regressing the returns of IBM against the S&P over a 30-year period. Here's my actual historical return for IBM. Okay, the actual historical value for the dependent variable. Okay, Y with that flat line above it, that's the historical average. Now remember, folks, these are only samples, the historical average, the sample mean, which is only an estimate of the actual population parameter. How good of an estimate is it? I don't know. What was the size of your sample? The higher the sample size, the lower the risk of sampling error. Then we've got Y with this funny looking symbol. What is that? That's Y, the predicted value of Y per our regression. Predicted value of dependent variable given our regression model. And what's going to be our regression model? Well, we're going to try to predict the value for Y, giving our Y-intercept, B subscript 0. I don't care if that number is 0. That just means the value of Y if the historical value of X was 0, your Y-intercept. plus our slope coefficient. How are we going to calculate that slope? Covariance divided by the variance of x, or change in the dependent variable given the change in the independent variable. Then times your independent variable plus your error term. Now, what is our error term? And I'm going to leave that off for a second. I'll talk more about the error term in a second. But look, we're only whoa, that's not good. We got shrinkage there. Can't have that kind of shrinkage. All right. So this is only a predicted value for y. There's an actual historical value for y. We hope that our predicted value of y per our regression equals the actual historical amount. But if there's an error, we hope it's very small. But anytime you're dealing with an expected value, we know sometimes the actual value is a little higher, sometimes it's a little bit lower. If you added up the unsquared errors, what would they sum to? 0. Okay, so the expected value of the error term is 0. All righty, now, isn't this exciting stuff? You ready? So our y-intercept, value of y if x is 0. How do you calculate that? That's a cliffhanger. I'm going to show you that. Value of y if x is equal to 0. All right, b subscript 1, we want to test that slope coefficient. We don't want that to be equal to 0. If the slope coefficient equals 0, that is bad. That's the financial term. Yes, that's bad. That means the slope coefficient is insignificant. You got a bad regression model. Okay, here's our independent variable x, and here's that error term. The expected value of the error term is what? 0. Sometimes it's more than, sometimes it's less than. The above, the below, add it all up, it'll sum to 0. Okay, so the error term is the difference between what? Actual historical y versus y per our regression. Okay, so the difference between the actual historical value for y versus what we predicted per our regression model. All right, look at this beautiful slide. We love drawing pictures here. You ready? Let's first talk about the explained movement in y. Okay, we're going to call that the sum of the squares of the regression. That is the sum of y per our regression minus the historical average value for y squared, the sum of the squares of the regression. Okay, now the estimated value of y, the y per the regression, well, that's per our regression model. So that is per this formula, okay? This is what we predicted y to be. But hey, man, sometimes we were almost right on the money, but look at that, a little error here. The actual historical value of y was a little bit higher than what we predicted. Sometimes the actual historical value of y was a little bit lower. These are the errors, folks. That's the unexplained. We're gonna call that the sum of the squares of the errors for our regression model. Okay, sum of the squares of the regression model. So that's going to be the sum of y minus y per the regression squared. That's the unexplained movement. All righty. Here's our y-intercept. The value, that is the value of y when x equals what? 0. So when x is equal to 0, that's what we would have predicted y to be. If the y-intercept could be 0, that doesn't invalidate your regression model. It's not a big deal. But if your slope coefficient is 0, that's a really big deal. So our regression model, here's what we think the y-intercept is, the value of y when x is 0. Here's our slope, the change in our independent variable, the change in our dependent. We've got 2 ways of getting that slope, and that's going to be step 1 later. So we could take the change in the dependent divided by the change in the independent variable, which in this example is 0.7245, or same result, different format. If we have the covariance between x and y, divide that by the variance of the independent variable. Another way to get your slope coefficient. Got it? All right, we're kicking ass, baby. Do you feel it? I feel it. I feel it. So here we go. You ready? Step number 1. I need my slope coefficient. So step number 1, we find our slope coefficient first. You don't have to worry about all the fancy math here. At the end of the day, how do we get our covariance? How do we get our covariance? You ready? The sum of the errors, it doesn't matter which variable you put first, the errors of y times the errors of x do not square anything. We multiply the errors all the way down year by year, add it all up. What's this denominator? That is the sum of the squares of the errors for your independent variable x. Okay, so covariance divided by the variance of x, the independent variable. Okay, so the sum of the squares of the errors, all righty, for the independent variable x. So there's your numerator. So at the end of the day, folks, you're going to find your slope coefficient, covariance divided by the variance of x, or they'll give you change in the dependent, change in the independent variable. All right, we get that slope coefficient first. Step 2, once you get your slope coefficient, there's your historical average value for y. There's your historical average value for x. So step 2, we're going to back into our y-intercept by taking that expected value for y, the historical average, minus what we think the slope coefficient is, times that average value for the independent variable. Okay, that's how you're going to find your y-intercept. All righty. Now, I just like to do right here. You don't have to worry about all of this covariance divided by the variance of the independent variable, or change in the dependent divided by your change in your independent variable. Okay, so steps 1 and 2, now we found our values. So b subscript 1, if that equals 0, not a big deal. Simply doesn't destroy our regression model. But folks, if our slope coefficient could equal 0, that's bad news, okay? So we're gonna wanna test, could that slope coefficient B1 equal 0? If so, that's bad, okay? We also wanna test, could the correlation coefficient, that correlation coefficient between x and y, could that equal 0? If it does, that invalidates your regression. We call it being insignificant. So you got an invalid regression. We don't care so much about the y-intercept being 0. We could test it, but we're more concerned about the slope coefficient, the correlation coefficient. We don't want those to be equal to 0. All right, so we're going to have something called the sum of the squares of the total. Okay, that is your numerator for the variance of y, the sum of the squares, actual minus expected, the error square at summit, your numerator for the variance of y. Then you're going to have the sum of the squares of the regression. This tells us the explained movement in y. What's explained by our regression, our movement in our independent variable. So if you take the sum of the squares of the regression, you divide it by the sum of the squares of the total, that is your coefficient of determination. Take the square root of r squared and you got your correlation coefficient. Okay, the unexplained, that's our errors. Okay, this is the movement in y that's not explained by our regression model. The sum of the squares of those errors divided by the sum of the squares of the total, that's equal to the unexplained, which is the same thing as 1 minus r squared. Same thing as 1 minus r squared. That is those errors. Here's what I predicted y to be per my regression. Here are those actual values. Okay, those are our errors. Okay, we want a tight confidence interval. We don't want the unexplained to be very large. Okay, so obviously, or maybe not so obvious. All right, do not memorize, folks. At level 1, like level 2, there's no writing of essays, there's no constructed response. It's about identify, recognize which of the following are assumptions of linear regression, or all of the following are assumptions of linear regression except. All right, so you don't have to memorize, you're not writing an essay. So we want a linear relationship, folks. So here's our predicted value for y, here's our independent variable. Hey, we would like to see a linear relationship, whether it's positively sloped or, like regression, your probability of passing against happiness, it could be an inverse relationship, a negative slope. Either way, we want there to be a relationship between the two. Okay, homoscedasticity. Homoscedastic, we do not want the size of the errors to vary with the size of the independent variable. What's bad is something called conditional heteroscedasticity. I'm just going to put down conditional hetero is bad. You know what that means? If we regressed our errors, if we regress the errors against the size of the independent variable x, what we don't want to see is something that looks like this, where the errors, I'm not an artist, as you could tell. Let's try that again. So here's our predicted value for y. We don't want it to be such that the errors are correlated with the size of the independent variable. That's called conditional heteroscedasticity. We don't like that. Homoscedastic is good. All the observations, my errors are pretty much constant. You know, on average, it kind of looks like that. All righty. I don't even mind if it's unconditional heteroscedasticity. You know, it's not exactly constant, but it doesn't vary in a way significantly with the size of the independent variable. Just remember for me, conditional heteroscedasticity is bad. We like homoscedastic. I want the size of the error, whatever the value of x is, it doesn't matter. The size of the error more or less stays the same. It does not vary in any kind of way with the size of that independent variable. Okay, now we do not want the pairs of y if we have multiple regression. Okay, we'll talk about later on multicollinearity and stuff, but that's for level 2. All right, the residuals are normal. What does it mean to be normally distributed? Theoretically goes from negative infinity to positive infinity, except in a regression, here's our predicted value for y. Okay, so the value of our error terms normally distributed. Okay, we do not want the size of our errors correlated with one another, nor do we want the size of our errors correlated with the independent variable. Okay, so we don't want what's called serial correlation. And you're going to learn in level 2, some guy named Durbin Watson likes to eat his cereal. And I'll talk to you a little bit about the Durbin Watson statistic, time permitting. Okay, R squared. We could either take our correlation coefficient, step 1, if we have to, covariance divided by standard deviation of x, standard deviation of y, and square it. Or what else could we do? We could take the sum of the squares of the regression divided by the sum of the squares of the total and get our R squared that way. R squared is known as what? Coefficient of determination. You've got to be able to calculate that. Okay, so that's on your must know. Anything that's a squared variable is going to have a value between 0 and positive 1. Okay, we want R squared, higher the better. We want a lot of the change in the dependent variable to be explained by the change in the independent variable. Okay, multiple R, what the hell is that? Well, that's the square root of R squared. Oh yeah, so if we go backwards this way, the square root of R squared, that is simply our correlation coefficient. You want to get fancy, we'll call it our multiple R. That has a range between what? -1, +1. Beautiful. All right, now the way we do our course, folks, we assume no prior knowledge. Okay, look, I don't know what you learned in school, I don't know what you forgot. So we assume you either never learned it, or if you learned it, you got a C, or if you learned it and got an A, you celebrated so long, so hard, you blacked out and forgot everything you learned. All right, so again, the videos are there, folks. We cannot assume. We got people who've taken quant, we have people who've never taken quant. I got marketing majors, I got accountants, I got engineers, I got scientists. I don't know who knows what. So you are always in good hands. We will never say to you in any video, oh, you should know. We don't take, this is not an executive summary, okay? Assuming you got an MBA. You might have an MBA, but how long ago did you get it? All right, how good was the program? I don't know, did you do it online? You know, so look, we got you covered. All right, so our explained variation, sum of the squares of the regression, the unexplained, the sum of the squares of the errors, the variance in y, the numerator to calculate the variance in y, sum of the squares of the total. That is the total variation in y, total variation in y. Okay, this numerator, be on the lookout for it being presented this way, what we predicted y to be versus that historical average squared, sum of the squares of regression. The unexplained, the sum of the actual historical value for y versus what we predicted per our regression model. That is the sum of the squares of the errors. And your numerator for the variance of y, the numerator for the variance of y, that is the sum of the actual value of y versus the average value of y squared. Folks, we add this up. The total sum of the squares, 102 plus your 2766, 130.31. 130.31. That is our sum of the square. That's our numerator if we wanted to calculate the variance of y. All righty, so what do they want here? They want multiple r. What is that again? Oh yeah, that's the correlation coefficient. Well, how are we going to get that? Step number one, I got to get my r squared, the sum of the squares of the regression divided by the sum of the squares of the total. So the 102.65 divided by the 130.31, r squared, 0.7877, pretty darn good. 78% of the movement in y can be explained, don't use the word caused, by the change in the independent variable. But that is not what they asked for. That is the most common wrong answer. Step two, they want the correlation coefficient. Oh yeah, square root of 0.7877, 0.887, correct answer, choice C. That is your correlation coefficient. All righty, so you don't want to make a silly mistake. Folks, what we do with every one of our answers, by the way, we give you detailed explanatory answers. We want, and what we do in the class, myself, Darren, the other instructors, like, look, I'll tell you, if 78% is explained, then obviously 1 minus 78.22 is unexplained. Those are your errors. How would we get those errors directly? Take the sum of the squares of the errors divided by the sum of the squares of the total. 130.31. That is the unexplained. We want the explained higher the better. We want the unexplained lower the better. All righty. So we do that with every single question. All right, now a t-test, the regression coefficient, specifically the slope coefficient. All righty. What do we think the value of the regression coefficient is? So what do we think B1 is, or B subscript 0? Okay, minus the hypothesized value. Could it be 0? Could it be 1? I don't know. They'll tell you what the hypothesized value is. Then you divide that by the standard error of the coefficient. That'll be given information. You do not have to calculate that. That'll be given. All righty. So in the example I'm about to show you, we think our slope coefficient is 0.7245. Okay, given information, the standard error for that slope coefficient is 0.0456. All right, so the null hypothesis in this example, hey, could that slope coefficient be 0? If so, that's bad. If you accept the null, that's bad news, folks. That means you have an invalid regression. The alternative hypothesis is no, B1 is not 0. Okay, that would be good. Folks, this is a two-tailed test. Two-tailed test. The actual value could be higher or lower. Okay, greater than 0, less than 0. Okay, so it's a two-tailed test. So I'm going to take 0.7245. That's what we think the slope coefficient is. That would be given information, or you'd have to find that. Your covariance divided by your variance of x, or your change in your dependent divided by whatever. Okay, so that would be something you'd have to calculate or given. Minus the hypothesized value. Hey, could it be 0? Maybe you have an invalid regression. Divided by the given standard error, 0.0456, 0.0456. This is called our test statistic. I like to call it our T calculated value. This is not something we look up. This is something we calculate. 15.88. All right, 15.88. Now, they have to give you a specific confidence interval or level of significance. So, folks, they're giving us a level of significance. Oops, sorry about that. They're giving us a level of significance. I just want a blank slide. A blank slide. Give me a blank slide. All right, let's do that. Okay, so sorry about that. Okay, so two-tail test, folks, our level of significance, 5%. Why is this two-tail? Anytime you're testing equal or not equal, your error could be in the left tail or it could be in the right tail. So folks, 5% of your level of significance, 1 minus the 5%, what's our bounded confidence interval? Our bounded confidence interval is therefore 95%. You should have memorized, folks, your z-value is exactly equal to 1.96. Z or a t-test. You ready? This is your reliability factor. Reliability factor. When your sample size greater than or equal to 30 and or the standard deviation of the population is known, go ahead and use your z-value. Otherwise, you've got to look up your T critical value. T critical. Okay, you'd have to go down degrees of freedom in the table. They begin an excerpt of the table. Sample size minus K minus 1. Okay, that's how far down you'd have to go in the table. Okay. So, or in this case, we only have one independent variable. So I'll show you an example and we'll actually apply it in a little bit. Okay, but how far down you go in your table, your degrees of freedom. Okay. So, oh, what the hell? I already told you, K is the number of independent variables. Okay, so if it's a simple regression, then obviously you have 1. So n minus 1 is the same thing as n minus 2. How far across you go in the table? Alpha divided by 2, because it's a two-tailed test. 0.05 divided by 2, 0.025. Cumulative probability of not being in the left tail is going to be 97.5. Okay, so we're going to have to look up our t-value. So let's say our sample size is greater than 30. Okay, let's say our sample size is greater than or equal to 30. So Z would be exactly 1.96. We'll just round it up to 2. So here's our critical value. T critical minus 2. T critical plus 2. If your test statistic, what I call that T calculated value, is within plus or minus 2, you must accept, you cannot reject, you must accept the null hypothesis that B1 is equal to 0. All righty, so what did we get? Well, when we did the test, 0.7245, our value, what we think the slope is, minus the hypothesized value, could it be 0? Divided by the given standard error, we got 15.88. That is certainly not within plus or minus 2. That's way out here. So folks, when you're way out here, you reject the null. That means we're going to accept, you know what? We think the slope coefficient doesn't equal 0. Hey, we think it's significant. Looks like we got a pretty good regression model. Okay, looks like we got a pretty good regression model. That's generally what we're going to do. But for whatever reason, the hypothesized value, folks, could be 0, could be 1. In this case, look at this example. Hey, what if we said the hypothesized value, somebody says, nah, you know what, the slope coefficient is not 0.7245. Somebody's saying, nah, I think it's exactly 0.7. Okay, so the null hypothesis is the slope coefficient is 0.7. The alternative is no, it is not 0.7. So we take what we think it is, our result, minus that hypothesized value divided by the given standard error. What do we get? 0.526. Now, folks, is that within plus or minus 2? At a 5% level of significance, you bet. We've got to accept, because 0.526, if that's 0, that's within. We've got to accept. The slope coefficient could be exactly 0.7. It could be. We cannot reject. We'd have to accept, you know what, that could be exactly 0.7. Now look, sometimes they will give you the critical value. Like here, you see 21 data points. Let me put in another slide, hold on. Okay, in this example, sorry about that. In this particular example, what did they tell us? There are 21 data points. So if sample size is less than 30 and standard deviation of the population is unknown, you must look up your T critical value, So how far down would we go? Well, if sample size is 21, it would be 21 minus the number of independent variables minus 1. 21, 20, 19. We'd go down 19 and we'd go across to 0.05 divided by 2. Now, if we had the table, this corresponds to a T value, check it out, 2.093. Notice the Z value is 1.96. Your T value, folks, is always going to be greater than the comparable Z value. It's always going to be greater than, because you have less reliable information, less reliable. Okay? So whether it's plus or minus 2.2 exactly or 2.093, it doesn't matter. Our test statistic, our T calculated value there was definitely within, whether it's 2.09 or just 2 within, so we cannot reject, we must accept. All right, beautiful. Time is flying. So much to do. All right, now a confidence interval, a regression coefficient. Now remember, we have in our example that we're still working here, get my big head out of there, our y-intercept was 3.09, B1 0.7245. Okay, so we're using those same facts. Now, anytime you see your sample size greater than or equal to 30, use your Z value. Okay, use your Z value. You have to have memorized those Z values. Remember, and I don't know where you are in your studies, but ones that you need to have memorized: 68% bounded, 16% in the left tail, 16% in the right tail. Your Z is equal to plus or minus 1. If you've got a bounded 90%, 5% in your left tail, 5% in your right tail, your Z value, 1.645. If you've got a bounded confidence interval of 95%, 2.5 in the left tail, 2.5 in the right tail, Z equal to 1.96. Excuse me. If you have 1% your left tail, 1% your right tail, bounded confidence interval, bounded of 98%, Z equal to 2.33, you're going to need that with value at risk in portfolio management. And then if you've got 99%, you got a 0.5% here, 0.5% there. Z is like really high, 2.8 or something like that, but I forget that one off the top of my head because I very rarely see it. All right, but that you got to have committed to memory. Okay, well, don't want that example yet. All right, so what we want to do is we have a point estimate, plus or minus a Z or a T value, okay? We're going to have a standard error that will be given information. You will not have to calculate that. Okay, we're going to want to draw a picture. This is what we think the slope coefficient is. Okay, so we could do this. We could draw this around our slope. We think it's 3.09 minus or plus our dispersion around that value. Okay, we could also do this for the slope coefficient. We think the slope is 0.7245. It could be less than that. It could be greater than that. Okay, we want to build a confidence interval. Confidence intervals are always two-tailed, always two-tailed. All right, so they tell us the standard error for the slope is 0.4645. That's for your slope coefficient. That's the standard error, 0.0465, excuse me. And then for our y-intercept, our standard error is 0.5434. Okay, so I want to build a confidence interval. Ready? You're going to take your standard error, and I'm going to do it here to keep it nice and neat. Let me delete that. Okay, you ready? So let's do it first for our slope coefficient. So we think it's 3.09. Okay, that's what we think our slope coefficient is using our calculation from earlier, 3.09. I want to build a confidence interval around that. I want to say, listen, I'm 95% confident that the actual y-intercept is in this range. I'll take my standard error given information for b subscript 0 times your reliability factor, t or z, and that'll get you your plus or minus dispersion around what we think the slope coefficient is, b subscript 0. Alrighty, so the standard error for the slope coefficient, excuse me, we'll do the y-intercept first. So the standard error given information, what did they say that was? 0.5434. 0.5434. Okay, let's say we have, we're using a t-value, we looked it up, 2.09. Okay, our sample size was less than 30, so we had to look up t, and I know it's given information 2.09. When in doubt, use 2. That's plus or minus 0.0973. So I'm going to take 3.093 to be exact, which was given. I'm going to subtract 0.0973. I'm going to add 0.0973. I'm going to come up with a range around our estimate for that slope, for that y-intercept. So we think it's somewhere between negative 1.137 or positive 1.137. We are 95% confident that the actual, if we looked at all the data, that the actual slope coefficient is somewhere in this range. Okay, so that's how we would build a confidence interval around that. Because remember, that slope coefficient is calculated using the historical average value for X, the historical average value for Y. Those are only sample estimates. So we think the actual population parameter, if we looked at all the data, would be somewhere in that range for the slope coefficient. Now we would repeat that process. Let's see. Review, delete ink. Just on that slide. All right, we think the slope coefficient is 0.7245. We got a sample size equal to 21. We know that our standard error given information for b subscript 1, that was given as 0.0465. All righty, so we think the slope is 0.7245. Whatever the change in the independent variable is, if the independent variable goes up by 1, we think the independent variable will go up by 0.7245. Okay, so that's our slope coefficient. Now, to build a confidence interval, the standard error for the slope coefficient times your reliability factor, T or Z, plus or minus dispersion around what we think that slope coefficient is. And we calculated that by taking the covariance divided by the variance of X, and all based upon what? Sample. This is the sample. It's only as good as the sample size. All right, so 0.04645, you do not have to worry about calculating that. That'll be given, times 2.093 plus or minus 0.0973. Remember, a confidence interval, two-tailed distribution of the error. The actual value could be lower or higher. All righty, so we're going to subtract 0.0973. We're going to add 0.0973. So we're thinking it's going to be somewhere between 0.6272 and 0.8217. All right, so we're 95% confident of what? That the actual slope coefficient, if we looked at all the data available, the population, we think the actual slope coefficient would be in that range. Okay, between 0.6272 and 0.8217. All righty. Okay, cool. Now, ANOVA, what does it look like? Here we go. Let's go. Look at what they give you. Multiple R. What's that again? Oh, yeah, that's your correlation coefficient. If that were not given, we would take the square root of 0.9589 the square root of r squared. R squared is what? Coefficient of determination. That is the change in the dependent variable. Explained, not caused, by change in independent variable. Okay, if that were not given, we would take 0.9793 and square it. Okay, the standard error of the estimate, I'm going to show you how to calculate that. Our sample size is 21. Okay, what's our number of independent variables? We regressed y against one independent variable. Our residuals, sample size minus 1. Okay, excuse me. Our sample size minus k minus 1. Our k is 1. 21 minus 1 minus 1, 19. And then for the variance of y, 20. Okay. Now, we've got our sum of the squares of the regression plus the sum of the squares of the errors. There's your sum of the squares of the total. They have to add up. If you have any missing piece, you've got it. What if they don't give you the average, the mean sum of the squares? Well, you're going to take the sum of the squares of the regression, you're going to divide it by 1, k, your number of independent variables. If they don't give you the 0.9106, that's the variance of our regression. You would take the sum of the squares of the errors divided by 19. That's how you get that. And then while they don't show it, if we wanted the variance for y, this is our numerator, 421.42, actual value for y, the sum of the actual value for y minus the expected value for y squared. That's our numerator. If you divide that by 20, you would get the variance of y. Okay, 0.9106, that is the variance of this regression equation. Lower the better. If they did not give us the standard error of the estimate, you see this? That is the square root of our variance. The square root of 0.9106. That is the standard error of the estimate. Lower the better. Okay, so F calculated, what the hell is that? This F calculated, that is called our global test of significance. The null hypothesis is all slope coefficients insignificant. Not a big deal when it's only simple regression, big deal in multiple regression. The alternative hypothesis, at least one slope coefficient is significant. Okay, if that 443.79 is not given, you're going to take the larger variance, the 404.12, divide that by the smaller variance, the 0.9106. That is your F calculated value, your F statistic. Higher the better. We want a small variance for the errors. We want that F calculated to be really high. That's excellent. So we would reject the null. That is not going to be within plus or the F critical value, which I'll show you later. Okay, so when F calculated is really big, that's a good thing. Okay, now, you ready? Our y-intercept, we think it's 3.09 minus, could it be 0? Divide that by the given standard error. What do we call that? Hey, that's that test statistic we saw before, 5.6921. That is not within plus or minus 2. We think the slope coefficient is 0.725. Could it be 0? Divide that by the standard error. Hey, 15.58. Not within plus or minus 2. So at a 95, well, at a 5% level of significance, at a 5% level of significance, we reject that the y-intercept equals 0 and that the slope coefficient. But the big one is that the slope doesn't equal 0. They both appear to not be equal to 0. And did we get 5.69 before? That number don't look familiar. Is that what we got? Let's see. The slope coefficient. when we did the slope coefficient, oh, I think I erased it. Let me do that again. So the slope was, I just did, that's because I only did it for the slope. I didn't do it for the y-intercept. Okay. Yeah, because it's not a big deal. If your y-intercept equals 0, that does not invalidate your model. It's not that big of a deal. Okay. A big deal is if your slope coefficient could be equal to 0. All right. So you got to find any missing piece of the puzzle. Okay. Regression, that is your number of independent variables. At level 1, we're looking at k equal to simple regression. All righty. Okay, now, multiple R is also known as what? Correlation coefficient. We got a couple ways of finding that. Square root of R squared, or covariance divided by the standard deviation of X times standard deviation of Y. That's another way to get your correlation coefficient. R squared, you could take the sum of the squares of the regression divided by sum of the squares of the total. Or you could take your correlation coefficient and square it. Okay, standard error of the estimate, square root of the variance of the regression model. Observations is n. K is your number of independent variables. Your regression, your residual, your errors, n minus k minus 1. 21 minus 1 minus 1. That's where we got degrees of freedom of 19. Okay, excellent. We are setting a good foundation. Okay, now the explained variation, higher the better. Okay, the explained, we want the unexplained, lower the better. The explained plus the unexplained, that's the sum of the squares of the total. All righty, so this was 404.12. The regression sum of the squares. The unexplained was 17.3. They just reversed the order. In the ANOVA table, it's the other way around in terms of order. Sum of the two, 421.42. Remember your symbols. This is Y per the regression versus your average value for Y historically. Okay? This is actual historical Y versus Y per the regression, what we forecasted Y to be given our regression model. And this is our numerator for the variance of Y. Okay, so if we took 421.42, divided that by 21 minus 1, we would get the variance of the dependent variable Y. Okay, now the mean regression sum of the squares, that was that 404.12 divided by K. And we got that to be obviously 404.12 because K in our example, one independent variable. The mean squared error, the sum of the squares of the errors, the 17.3 divided by N minus K minus 1, 17.3 divided by 19, 0.9105, 0.9105. Okay, you got to be able to recognize and fill in. And this is important, folks, because this is going to follow you to level 2. F-test, global test of significance. Take your larger variance divided by the smaller variance. That's all you got to remember in your regression model. Okay, your larger variance divided by your smaller variance. All right, your coefficients, what we think the y-intercept is and what we think the slope is. Okay, now that'll be supplied in the problem, but I'm going to show you how to calculate it if it's not. Standard errors for B subscript 0 and B subscript 1 will also be what? Supplied. Okay, so what we think the value of the regression coefficient is minus the hypothesized value. Could it be 0 or 1 or any other value they give you, or any value that is given? They might say, hey, could it be greater than 0? Remember, the null hypothesis always has to include equality. So anytime you're doing hypothesis testing, if somebody makes a claim, hey, I think the slope coefficient is greater than 0, that has to be the alternative, and then less than or equal to 0 would be the null, because the null hypothesis has to include equality. Okay, so this is everything we just did. Again, one more time, missing pieces of the puzzle. Okay, so this is your correlation coefficient. We know we have two different ways of calculating that. Covariance divided by standard deviation of x times standard deviation of y, or the square root of r squared. So you got two choices there. If you're given the correlation coefficient, just take your correlation coefficient and square it, or sum of the squares of the regression divided by sum of the squares of the total. Standard error of the estimate, what is that? That is 0.9106, the variance of the regression. That is the variance of our regression. Okay? The standard error of the estimate, the square root of the variance of our regression. So if you took the square root of 0.9106, you would get 0.9543. Lower the better for the standard error. R squared, higher the better. Observations, we always want n to be higher. The probability of making type 1 and type 2 errors goes down when you have a high sample size. Your probability of sampling risk goes down. Notice, k, n minus k minus 1, n minus 1. They have to add up. 404 plus the 17, there's your numerator, okay, for your variance in y. All righty. So everything there we've covered. Beautiful. Let's try a practice question. Now, our course embeds practice questions in the pre-recorded videos. And then we do these problem-solving seminars where we work blue book, get this, blue book examples in the actual CFA Institute reading, or questions at the end of the chapter of the CFA Institute reading. We pick the harder ones to do with you, and then you have lots more to practice in our software as well as in the CFA Institute materials, okay? But we want to break it down to make sure you know how to do it. And it's not just about getting it right. We don't have all day to get this right, so we got to make sure we're getting it right in a reasonable period of time. All right, let's see what we got. They tell us you're given the following information from an ANOVA table. Multiple R, there's my correlation coefficient. Standard error of the estimate, 1.4973. That's the square root of the variance of the regression. Total variation, 19.41. All right, so watch how I play with this information for a second. They want the F statistic. I know I'm going to need my larger variance divided by my smaller variance. But watch how I play with this. You ready? I want to set up my ANOVA. K at level 1 is always going to be 1. N minus K minus 1, your degrees of freedom for your errors, and then N minus 1. Okay? Here's the sum of the squares of my regression. Here's the sum of the squares of the errors. Here's the sum of the squares total, or TSS, whatever you prefer. Divide that by K. There's your mean. Divided by N minus K minus 1. There's your mean squared errors. All righty, now they gave me 2.2419. Okay, I just gave it to you. They gave me the standard error of the estimate. That's the square root of the variance. So we just work backwards. So let's take the standard error of the estimate, square it. What's our variance? 2.2419. 2.2419. Okay, so we got one piece of the puzzle. Okay, they also gave us our correlation coefficient, 0.8527. Now, if we take 0.8527 and square it, we get R squared. What's 0.8527 squared? That's 0.7271, agreed? Which can also be calculated by taking the sum of the squares of the regression divided by the sum of the squares of the total. Okay, now they gave me the total variation as 19.41. I'm given my denominator was given. Now we solve for R squared. Now we could find our numerator. 19.41 times 0.7271. What's got to be my numerator, the sum of the squares of my regression? That's got to be 14.113. Agreed? So the sum of the squares of the regression's got to be 14.113. The sum of the squares of the total, and I'm just going to move, I just want to keep it consistent with the way it was before. I just want to keep everything on the same side. Sum of the squares of the regression, sum of the squares of the errors, sum of the squares of the total. So the sum of the squares of the regression, we just said 14.113. We calculated that above. Sum of the squares of the total, 19.41. That was given information. So we could back into then what our missing piece of the puzzle here's got to be, because the sum of these two has to equal 19.41. So 19.41 minus 14.113, what's got to be the sum of the squares of the errors? 5.297. All righty. Now we're going to divide this by 1. Okay, that's going to be 14.13. All right, that's our larger variance, 14.13. We've already said they gave us the standard error of the estimate. We squared it. There's our variance of the regression. So F is our larger variance, 14.13, divided by our smaller variance, 2.2419. What is our F calculated value? It's got to be 6.3. 6.3. All righty. So 14.13, larger variance divided by your smaller variance. So your job pretty much at level 1 is to be able to manipulate that ANOVA table and find any missing pieces of the puzzle. Okay. Let's see what else we got. And there's our answer, nice and pretty. Okay. Now, sometimes, let's see. I'm going to put well, let's do prediction interval. That's greater than the standard error of the estimate. Why? The standard error of the estimate accounts for one potential error. Okay, one potential error. What's that one potential error? Our slope coefficient and our y-intercept are only estimates of their actual population parameters. Okay, your prediction interval accounts for two sources of potential errors in our model. Okay, number one, y-intercept and the slope coefficient are only estimates of their actual population parameters. And number two, relationships tend to change over time. So the relationship between X and Y, what that was historically, may not be what that relationship is going forward. So if you want to draw a confidence interval around a predicted value for Y using an actual historical value for X, you take the standard error of the estimate times your T or Z value, like we did earlier. That's your plus or minus around that predicted value of Y. But with a prediction interval, if you want to draw a confidence interval around a predicted value for Y given a forecasted future value for the independent variable, use prediction error. Okay, so we would have to take the square root of the variance, multiply that by your T or Z, and then that would be your plus or minus dispersion around that predicted value of Y. Your prediction error looks like that, is always greater than the standard error of the estimate. Again, why? Because the standard error only accounts for one problem with the model, and that's your slope coefficient and your y-intercept. You know what? Those are only estimates of their actual population values. Whereas the prediction error accounts for two sources of error. Yes, B subscript 0 and B1 are only estimates of their actual population parameters, and those are historical values. Okay, relationships can change going forward. Now look, people always ask me, Pete, do you have to memorize this formula? I would say no. Theoretically, could it be tested? Yeah, but the point value is so minimal for the time and effort. It's, you know what, when you take our course, like we're going to tell you, like you got to know CAPM, you got to be able to calculate weighted average cost of capital, you got to be able to do the indirect method for the statement of cash flow, you got to be able to calculate duration. I mean, there's certain things that are just must know. ROI safety first, the Sharpe ratio, okay, M squared, you know, there's just certain things that, yeah, core concept. But this, you know, this formula, look, if you got no family, no friends, no pet, I guess go ahead. But if you got any of the above, you know what? They're likely to give it to you. They're likely to give you the variance of the prediction error. Just remember to take the square root of that before you use it. This is what you got to be able to use it. Okay, that's more important than memorizing that formula. Okay, but we cover our bases. You ready? Just in case. Hey, 95% confidence interval for Y when X is 0.8% is closest to what? All righty. So 0.8%. So here's the information we're given. You ready? They tell us the expected value for X, Y per, now this is the value of Y using our regression model. Standard error of the estimate, 0.041. And then 0.24%. Okay, so there's our variance of X at 0.24, and then we're going to calculate the standard deviation. So let's do this. Let's take it step by step. You ready? So our variance for X, 0.24 squared. Okay, that would be 0.0576, 0.0576. Okay, and this is the sample standard deviation for X. I think I misspoke. Sample standard deviation for X. All righty. Now, they tell us, hey, we think the y-intercept is 0.11. We think our slope coefficient is 0.85. Okay. Now, our variance for X, the independent variable, how would we get that if we had to calculate it longhand, just out of curiosity? What's another way to get the variance of X? I know they gave me the sample standard deviation. How would we get the sample variance for X? How would we get that sample variance? Well, the sample variance, if we had to calculate it directly, we know it's 0.0576. The actual value for Y minus the actual, the historical average, the sum of the squares of the errors divided by our sample size minus 1. Okay, our sample size minus 1. Okay, so let's make our number of observations 30. So we can use our Z value. We have a pretty good sample size. All right, so my denominator would be 30 minus 1, 29. What would my numerator therefore have to be? The sum of the squares of the errors for X. You ready? If you take 29 and you multiply it by 0.0576, what do you get? 1.6704. All right, there's our numerator. Okay, X, let's call this a future value, a predicted value, a future value, a predicted value for X. Let's make it not an actual historical. So I don't want to use standard error of the estimate. I want to show you how to calculate my prediction error. So I'm forecasting that my prediction error has got to be greater than 0.041, because that your standard error of your estimate. Why? Because it accounts for 2 sources of error. Okay, so if we had to calculate that prediction error, if you got no family, no friends, no pet, or if you got a goldfish and you drowned it, you got nothing else to do, how do we do that? You ready? We want the square root of 1 plus 1 over n plus your numerator, the actual value for X, minus the expected value for X, the sum of the squares of the errors, okay? So the sum of X minus X squared. All right, so this denominator here is 1.6, I just got, there we go, 1.6704. Now I want an error. You ready? So we think the value of X is 0.8, given information. We think the value is 0.8. All right, so 0.80 minus the average value for X, given information, 0.57. Oh, sugar. Let me just make this a little bit neater. So that is what we think the value is minus the historical average squared. So we think X is 0.80 minus the average historically, 0.57 squared. All righty. Our sample size is 30. So we want the square root. This is why this is ridiculous, okay? And let me just move this over. The standard error of the estimate times the square root. All right, standard error of the estimate was given information 0.041. Okay, so we want the standard error of the estimate 0.041 squared times the square root of 1 plus 1 over n plus what we think the value of the independent variable is minus the historical average squared, that error squared divided by the sum of the squares of the errors, which we backed into knowing our sample variance is 0.0576. So divided by n minus 130, so we inferred that that's got to be 1.6704. You got to love it. So folks, we come up with a prediction error. And I'm just going to do this here. Look at this math. I mean, it gets nuts. So let's see. A prediction error. Oh, I can't read my own damn handwriting. Sugar daddy, yo. Come on, man. Well, a prediction error plus or minus. I can't believe I can't read my own handwriting after all that. Oh, sugar. Oh man. Well, let me do this. This is what we think it is. All right. The confidence interval. Sugar. Well, our prediction error times T or Z, we're just going to make that 2. Let's see, prediction error time, that's plus or minus. All right, let's see. Let me take a step back here. Let me do our, we got no room. Let me put another slide in here. Sorry, folks. Insert, let me insert a new slide. You see, you got to make sure you write neat. Darn it. All right, so get that. All right, here we go. So Y per our regression model. Okay, so Y per our regression model. Here's our regression model, given information, keep it nice and neat. So we think the Y-intercept again is 0.11%, given information. We think the slope coefficient is 0.85, and now we are inserting a value for X. Remember, this is not a historical. This is a future. This is a predicted value for X. Predicted value for X. So when you take, I got to do it real time. I'm sorry, folks. Darn it, bad handwriting. Shame on me. You ready? So let's take 0.85, enter 0.8 times, enter 0.11 plus. So we think Y per our regression model is 0.79, okay? So if we take our prediction error, we multiply that by our reliability factor, T or Z. This is the plus or minus dispersion around our predicted value for Y given forecasted X, not an actual historical value. Okay, so plus or minus. All righty, so let's see. It looks like our prediction error is 0.0423, 0.0423. That's our prediction error. So 0.0423, let's multiply that by 2. 0.0423 times 2. That is 0.08, and technically we're going to use exactly what the book used. Well, let's just do 2. 0.0864, 0.0864. So this is our prediction error, likely to be given, because as you could see, this is insane to calculate, but we predicted a value for y per this regression model of 0.79. So let's add, what is it, 0.0864, 0.0864. Let's subtract 0.0864. Let's see what we get. 0.79. 0.79, enter. 0.0864 minus 0.703. 0.703. 0.703, and then 0.79. 0.0864 plus 0.876, 0.876. So folks, we are 95% confident, 95% confident that y, that actual y will lie in this range. Okay, given that forecasted value for x. So 0.70, so hopefully that's an answer choice. 0.703 and 0.876, 0.703, 0.876, choice A. All righty, so when we worked this crazy formula, your standard error of the estimate squared, so all we're doing is applying this nasty formula, and that should be standard error of the estimate, 0.041 times the square root of 1 plus 1 over n, the whole thing, 0.0432. All right, that was our prediction error. Sorry about that, folks. So that's why that's likely, I just made the point for you why you don't want to memorize that formula. Because even if it were an open book test and you got it in front of you, you probably can't even freaking read the damn thing. All right, so that is our 0.041 squared times the square root of 1 plus 1 over n. All right. So when you predict a value for x, do not use standard error of the estimate, okay? If they give you a forecasted value for x, you use your prediction interval to get your confidence interval. All righty. Now, let's see. Okay, so now the next thing I want to do is a nice, beautiful, this actually comes from a sample question in the actual CFA Institute, folks. So this is beautiful because now you're going to see what an actual, this is what our live, our problem-solving webinars are going to take really difficult questions from the CFA Institute reading and do it with you. All right, so here's an example. They tell us here, we got a number of statistics in Exhibit 1. Okay, we'll deal with that in a second. Here's all the information that they've given us, okay? What I want to do is set this all up for you. All right, so let's read through it. Ann Liu is an analyst researching whether a company's debt burden affects an investor's decision to short the company's stock. So the debt burden would be what? Our independent variable. And then whether or not we should short the stock, that's our dependent variable, okay? So we set that up. They tell us she calculated the short interest ratio, the ratio of short interest, times or whatever, for 50 companies. So our sample size is 50. Okay, now they give us the following information. Okay, here's our debt ratio. Again, what is our debt ratio? That is our independent variable. What's the 19.855? What is that? The sum. It's not the sum of the squares of the errors. It's just the sum of all of the values we looked at for the independent variable. And how many values did we look at for both x and y? 50. So folks, this is our numerator to calculate the expected value for X, the average value for X given the 50 companies we looked at. So we added up all the values for X. What sample mean did we get? Divide that by 50, we get 0.3971. That is the average value for X, at least historically. That's the sample estimate given the 50 companies we looked at. Short interest ratio, that's our dependent variable. This is Y. I want my average value for Y. So when we added up all 50 companies and we added up the short companies, okay, we got 192.3. Divide that by your sample size, 50. Now we've got the average value for Y, 3.846. Okay, cool. Sum of the squared deviations from the mean, the actual minus the expected value squared. We're summing the squares of the errors. That's our numerator to calculate variance. So the variance of X, you ready? I'll do it over here. The variance for X, I need the sum of the squares of the error, the actual minus the expected value, 0.3971, get the error, square it, sum it. We got 2.2225. Divide that by our sample size minus 1. What's our sample variance? 0.0454. The square root of our sample variance, that would be our sample standard deviation. So we think the standard deviation for X, the sample, is 0.213. Do the same thing for Y. The variance of Y, the sum of the squares of the errors for Y, 412.2042 divided by our sample size minus 1. I got the variance for Y to be 8.41. Take the square root of 8.41. Here's our sample standard deviation for Y. I got that to be 2.9. Okay, what's the sum of the cross products of the deviations from the mean? The error of X, don't square anything, times the errors for Y. We take the error of X times the error of Y. Each and every year we go down the list, sum the product of the errors of X times the errors of Y. Oh, sugar, that's way too big. Let's try that again. This is our numerator to calculate covariance. Our numerator to calculate covariance. The sum of the errors of X times the errors of Y. Now, if we divide that by our sample size minus 1, what do we think covariance is? A negative 0.1886. That's what we think the numerator, not covariance. Oh, excuse me, that is our covariance. The 9.243 is not covariance. That's the numerator for calculating covariance, okay? Then you got to divide it by your sample size minus 1. Now remember, covariance doesn't give you the strength of the relationship. It just tells you the direction. So we think the relationship between the dependent and the independent variable, we think that's inversely related. So that when the independent variable goes up, the dependent variable goes down. We think our slope coefficient is negative. The strength of the relationship is measured by what? Your correlation coefficient. Your covariance divided by the standard deviation of X times your standard deviation of Y. And I know it's a sample. We didn't look at all the data. So sample standard deviation for X and Y. Okay, so let's find it. Negative 0.1886 divided by standard deviation of X, 0.213, times the standard deviation of Y, 2.9. I got that to be, come on, man, negative 0.3054, negative 0.3054, I believe, negative 0.3054. You know, man, oh, Sam, I got to take a handwriting class. 0.1886, change the sign. 0.213, enter. 2.9 times divided by negative 0.3054. So folks, that's what we think our correlation coefficient is. Now let's square that. What do we think R squared is? Only 0.093. That is crappy. So the sum of the squares of the regression divided by the sum of the squares of the total, This is a horrible regression model because only 9% of the movement in the dependent variable is explained by the independent variable. Now, let's find for ourselves our slope coefficient. You ready? Covariance divided by the variance of x. All right, that is our slope coefficient. Negative, and that should be a b subscript 1, I'm sorry. Negative 0.1886 divided by the variance of x. 0.0454. I get the slope coefficient to be a negative 4.15. Now let's find our y-intercept. What do we think the y-intercept is? The historical average value for y minus the average value for x times our slope coefficient. So the average value for y, 3.846, minus the average value for x, 0.3971 times our slope coefficient, negative 4.15. We think our y-intercept is 5.49. So folks, we just created our regression model. Okay, we just created our regression model. So our regression model, you ready? We just created, we're gonna predict the value for y. What do we think our regression model is? We think our y-intercept is 5.49. We think the slope coefficient is negative 4.15 times whatever the independent variable is, x. All righty? So that's what we think. Now, if you want to put parameters around that predicted value for y, looking at actual historical information, then you take standard error of the estimate. That's plus or minus using a historical value for x, using historical x, an actual historical value, versus prediction error, which is always larger than the standard error of the estimate. Don't ask me to calculate it again because I won't do it. That's plus or minus your predicted value of y using a forecasted value for x. And now we've got two sources of error. First of all, your slope coefficients are only estimates because we didn't look at all the data. We only looked at a sample, and those relationships between x and y could change over time. Okay, so there we go. So that's that. All right, so now we got our regression model. Okay, let's see what else we got. So now they tell us, oh, I'm sorry, there we go. So k, our number of independent variables. Then we've got 50 minus k minus 1, 48. Then we got 50 minus 1, 49. 48 plus 1, there's your 49. Here's the sum of the squares of my regression. There's the sum of the squares of my errors for the regression model. There's the sum of the squares of the total. Okay. So now, if they did not give me r squared, by the way, is that the same number we got a second ago? You bet it is. By taking the covariance, dividing it by the standard deviation of x, we got our correlation coefficient. We then squared it. We got the same number. Or what's another way to get that value? Or you can get that value. Or we could get that value by taking the sum of the squares of the regression, 38.44, dividing it by sum of the squares of the total, 412.20. Sum of the squares of the regression divided by the sum of the squares of the total. Okay, this is our explained movement in y, which is not a lot. This is bad. And there's our unexplained, the errors, the movement in y that has nothing to do with x. Horrible. All righty. Now, standard error of the estimate, 2.7905. What if that were not given? Then we would take the square root of 7.7867, our standard error of the estimate, 2.79. Okay. Now, 38 explained, 373 unexplained, 412.2042. Now, if we take the sum of the squares divided by your degrees of freedom divided by 1. If they didn't give you the 38, you could find it. The sum of the squares of the errors divided by n minus k minus 1. Divide that by 48. If they didn't give you the variance of the regression, you could calculate it. And let's see if we got the variance of y correct. The 412 divided by n minus 1, 49. the variance of y, 8.41. That is our variance for y, the dependent variable. Is that what we got when we did it the other way? Let's see. Variance of y, whoop, there it is. Thank goodness. I gotta save some face, baby. I almost lost you. That damn prediction interval. I'll tell you the truth, I didn't memorize that for level 1. I didn't, as you could tell. All right, so n is equal to 50. What else can we do? All right, so F calculated, global test of significance. F calculated, larger variance divided by that smaller variance. Okay, our larger variance, 38.44, mean sum of the squares of the regression, mean sum of the squares of the errors, 7.7867. F calculated, terrible, 4.94. That's really low. Okay, so it doesn't look like we're going to pass that global test of significance at all. Okay, so there's our F statistic, our F calculated. The mean sum of the squares of the regression divided by the mean sum of the squares of the errors. That's a big mean sum of the squares for the errors. The larger that is, the lower your F calculated. A low F, a low T is bad. Low F, a small f, a small t, that's bad. Small f stat, small t stat, that is bad. Okay, that's bad stuff there. We don't like that. Okay, so let's see what we got. They tell us, let's see, did we get it right? Here's the y-intercept. There's our slope coefficient. So 5.4975, 5.49, and negative 4.15, our slope coefficient, negative 4.15. So there we go. So here's your y-intercept. Here's your independent variable x. That was our debt ratio. Shorting is dependent upon that debt ratio. We think the relationship is inverse. Now, could the coefficients be equal to 0? I don't care if the y-intercept is 0, but I do care. And by the way, since our hypothesized value is 0, you really don't have to put that in there, but I'll just put it in. There are our test statistics, okay? So it looks like our y-intercept is significant. That is not within plus or minus 2. Now, would you have to look up? We could use a z-value here, okay? Since our sample size is greater than or equal to 30, you can go ahead and use your z-value with a 5% level of significance to tail. Your z-value plus or minus, we would round it to 2. Negative 2.2219. Okay, so is that within plus or minus 2? No, so it actually looks significant. I mean, it's pretty surprising, but that is not within plus or minus 2. Not within plus or minus 2. So we would say, hey, that's significant as well. Barely, okay, but it looks to be significant. All right, now let's take a look at some questions. There are 3 interpretations of these results for her report. Companies' higher debt ratios, I don't like the word cause. They might explain, but we don't like the word cause. Companies' higher short interest rate, first of all, higher debt ratios was the independent variable, the short interest was the dependent. I don't like interpretation 2 is wrong for 2 reasons, because they got this backwards. The short ratio is explained by the debt ratio, not the other way around. Okay, so interpretation 2 is bad on both fronts. Companies with higher debt ratios, independent variable, tend to have lower short interest ratio. Interpretation 3 looks correct. Why? We had a negative slope, All right, inverse relationship. As the dependent variable, in this case, as the independent variable goes up, as that independent variable goes up, the dependent variable would go down. Okay, so this is the debt, this is the short ratio. I'm backwards. The independent variable is the debt ratio, the short ratio is the dependent. As higher debt ratios, yeah, we're likely to see an inverse relationship. All right, now she is especially interested in using our estimation to predict the short ratio, which has a debt ratio of 0.40. So we want to predict, we're going to use your model. We set up our model, so 0.40. You ready? Let's plug it in. Where was our regression model? There it is. So now 5.49 plus a negative 4.15. What did they say the independent variable should be? Positive 0.40, right? Watch your signs, folks. Watch those signs, okay? Positive 0.40. So I would predict the value, the short ratio, to be 3.83. 3.83. So using our regression model, that would be our predicted value for Y. Okay, now remember, that's only a predicted value for Y given our regression model. We got a Y, and we're inversely related, so I'm already starting off wrong. There's Y, there's X. We've got an inverse relationship, okay, between the two. So as that independent variable goes up, the dependent variable 3.83, okay, with a y-intercept of 5.49. Okay, what else do they tell us here? Let's see. Based on exhibits 1 and 2, if Lou were to graph the 50 observations, the scatter plot summarizing this relationship would best be described as what? Well, a negative slope, downward sloping. Okay, so that would be downward sloping. All right, so your dependent variable, your short ratio relative to your independent variable, your debt ratio, negative slope. Okay, so let's see what else they tell us. Based on exhibit 1, the sample covariance, remember that? Covariance. The sum of the errors of X times the errors of Y divided by your sample size minus 1. Okay, this was given information. They gave us that numerator, not negative 9.243, sample size 50 minus 1, negative 0.1886. That was our covariance, okay? Now, is there another way to get covariance? Yes, sometimes you have to back into covariance by taking your correlation coefficient times your standard deviation for your independent variable times your standard deviation for your dependent variable. Our correlation coefficient, we got 0.3054, and it's got to be negative because we know our covariance is negative. We know the relationship is inverse. Standard deviation for X was 0.2129. We calculated that. Standard deviation for Y was 2.9. So covariance, same result, different format, negative 0.1886. Woo, baby. All right. Let's see. Based on exhibits 1 and 2, they want to know, hey, what's the correlation between the debt ratio and the short interest ratio? Okay, so we have the square root of R squared. That's one way to get our correlation coefficient, or correlation coefficient, covariance, standard deviation of X divided by the standard deviation of Y. We know that our correlation coefficient, negative 0.3054. If covariance is negative, then your correlation coefficient is negative. If the numerator, the sum of the errors of X times the errors of Y, no squaring. Okay, if the numerator is negative, that's your numerator to calculate covariance. If that numerator is negative, then your covariance is negative, which means your correlation coefficient has got to be negative as well. Okay, so the square root of R squared, again, R squared being the sum of the squares of the regression divided by the sum of the squares of the total. The problem is when you take the square root of R squared, you're not going to know if you're dealing with positive or negative unless they give you information about the relationship between X and Y. R squared is always positive, as we know. We know that R squared always has a range between 0 and positive 1 being a squared variable. So you can't just take the square root of R squared and say that's your correlation coefficient. Not that easy. You got to delve into the facts to see, hey, you know what, positive or negative. Okay, which interpretation? Remember, change in it's the change in the dependent variable explained, not caused. by change in the independent variable. Explained, okay, tendency, what happens, what we tend to see. So explained the tendency, just like, when you do a hypothesis test, it doesn't guarantee, it doesn't prove anything with 100% certainty. It's what's likely to be true or false, what we've viewed historically. Okay, the dependent variable in Lew's regression analysis was what? What was the dependent variable? Well, how often the short interest ratio is affected by what? The debt ratio. The debt ratio is the independent, short ratio is the dependent variable. What else? Let's see. Based on Exhibit 2, the number of degrees of freedom for the t-test for the slope coefficient. Folks, your t critical value, your slope coefficient, your degrees of freedom, your sample size minus k minus 1. We're dealing with simple regression at level 1, so k is always equal to 1. So 50 minus 1 minus 1, that would be what? 48 would be our degrees of freedom. How far across we go in the t-table? 0.05 divided by 2, 0.025. The null hypothesis, could the slope coefficient be equal to 0? The slope coefficient is not equal to 0. Two-tailed test, what does that look like? Okay, two-tailed test, 2.5%, 2.5%, -2, +2. Okay, we need our test statistic. What did we think the value of the slope coefficient was? We thought the slope was -4.1589. That's what we thought the slope coefficient was, right? Minus the hypothesized value. Could it be 0? Divided by the standard error, which is given information 1.8718. What did we get? -2.22. If it were in this range, we'd have to accept the null. Okay, but because -2.22 is outside, it's a little bit outside, what are we going to do? Reject the null and accept the alternative. We think the slope coefficient is significant. Okay, so that's one way of testing your slope coefficient. Then we have the f-test. Okay, then we have our f-test. Okay, but before we do the f-test, which of the following should Lew conclude from the results? The average short interest ratio, 5.4975. That was our y-intercept. Okay, 5.49, that's the value of y when x was 0. Okay, when x was 0, the value of y was 5.49. Okay, so that's incorrect. That's not the average short ratio. That's the y-intercept. And remember, the short ratio, that was our independent variable. Okay, we got, what did we get that to be? We got the average value for x. We calculated way back like 20 minutes ago when we started this problem. We said the average value for x, 0.3971. That's the historical average value for the independent variable, 0.3971. Okay, the estimated slope coefficient is different from 0 at the 5% level of significance. True. That's what we just proved on the prior page. Okay. The debt ratio explains 30.54. No, it does not. It does not explain 30.54. R squared was only 9.33%. It only explains 9.33% of the variance in the short ratio. Okay, so C is incorrect. So B is the correct answer there, as we just saw. Okay, now what did we predict? Given a value for X, if we say X is 0.40, so the predicted value of Y, given that value for X of 0.4, we would predict Y to be 5.49 plus that negative 4.16. That works out to be 3.83, choice A. That is our predicted value. Okay. All right. You got 1 second, 1 minute, 1 second. I'm going to be right back. I just got to let somebody in my door who's been waiting patiently. So hold on, give me 1 second, 1 second. Don't go anywhere, don't go anywhere. Be right back, 1 second. Sorry. Did you see me in my shorts? Did you get me? Sorry about that. Let me put my mic back on. See how patient? Patience is a virtue. All right, we're teaching patience. Okay, let's see. There was one other thing I wanted to do with you guys, and I'm going to put this on a blank slide for you. Let's see. There was one more thing I wanted to do. Let me just put this back on. One more thing I wanted to do. Let's see. Let me just go through my notes, and I want to give you guys, see, even though it's free, I can't shortchange you guys. So let me put a new slide in here. There's one more I want to give you. Okay. Let's see. Where is one more. Sorry, folks, one more time. Just going through. I know there was something else I wanted to discuss with you guys. Covered F calculated that global test of significance. Okay, let's see. What else? One more thing, and then we'll open it up for a little Q&A, Sam. We'll open it up for a little Q&A. Did I actually cover everything I wanted to? I mentioned type 1 error, type 2, yeah. All right, yeah, there was one more thing I wanted to do. So we do not want the slope coefficient to be equal to 0, okay? We hope our T statistic is not within plus or minus 2. That's good, okay? We don't want our slope coefficient to be 0. We hope, we want F calculated, our F statistic, that larger variance. This is a big deal with multiple regression, but it is in the reading for level 1. We want our F stat to be greater than our F critical value. That means B1 is not likely to be 0, okay? So that's good. The other thing we can test is our correlation coefficient. I didn't cover that. Another type of test, could your correlation coefficient be equal to 0? That would be bad. That means there's no relationship, there's not a linear relationship between X and Y. Okay, that would mean no linear. There could be a nonlinear, but there's no linear relationship between X and Y. It could be nonlinear, but we want to see, is there a linear relationship? So our correlation coefficient. We don't want our correlation coefficient to be 0. Now in portfolio management, you want the correlation between your investments, if you're looking to diversify, to be closer to 0, or if you want to maximize diversification benefits, even be negative, okay? But in regression, a correlation coefficient of 0 is bad, okay? Because obviously if you take 0 squared, that means changing the dependent explained by 10, but it's changing the independent 0, so we don't want that. Okay, so we can do a test statistic for our correlation coefficient. What we think the correlation coefficient is, divided by the square root of the sample size minus 2, divided by the square root of 1 minus r squared. Okay, so this is a t-test. Okay, this is a t-test. So let's do that in this question. Let's find what was our correlation coefficient. Stick with me. Our correlation coefficient was negative 0.3054. So let's calculate negative 0.3054 divided by the square root 50. Our sample size minus 2 divided by the square root of 1 minus r squared. Now look, sum of the squares of the regression divided by the sum of the squares of the total, that's r squared. We're looking for 1 minus r squared, or you could take the sum of the squares of the errors divided by the sum of the squares of the total. So let's do it. Let's go back to our ANOVA, because we love our ANOVA. ANOVA, don't you know? There we go. You ready? So let's find the sum of the squares of the errors. Sum of the squares of the errors, 373, divided by sum of the squares of the total, 412. What is the unexplained? So 373 divided by 412. Here we go, here we go, here we go. So come on, man, 373, enter 412 divided by, that is approximately 0.91, which makes sense because our R squared was 0.09. So 1 minus 0.09, 0.91. That is our unexplained, okay? So let's take that unexplained square root of 0.91. 0.91. Sorry. We're all the way down here. Let's see. No, we're not. Where did we go? Where did we go? Oh, there we go. Okay, so that is 1 square root of 0.9, square root of 1 minus r squared. So 1 minus r squared is 0.91, 0.91 g square root 0.954. We'll make the denominator 0.954. So what is our test statistic? Let's take 0.3054, change the sign, times the square root of 48. I got my numerator to be negative 2.11 divided by the square root of 1, enter 0.91, minus enter g square root. So 1, enter 0.91 minus 0.09, enter g square root 0.30, enter g square root. Come on, man. 1 minus r squared. So 1 minus 0.91. So the square root of 0.09 g square root. So that is that 0.30? That's, I keep getting 0.30. So that is the square root. So 2.11, change the sign, enter 0.3 divided by 7, negative 7. So our test statistic, approximately negative 7, right? Is that what you all got? Sam, is that what you got? Sammy boy.
It is.
Is that what you got, for real?
Yeah.
Oh, thank you. So we got a test statistic of a negative 0.7. All right, so that is our test statistic. So this is also a t-test. All righty, so this is not within plus or minus 2. All right, so let's see. Do I have any more room here? So again, plus or minus 2, we got a t-test, negative 2, plus 2, that's an ugly plus, plus 2, we'd have to accept that our correlation coefficient equals 0. Again, two-tailed test. We got, let's see, we got a test statistic of, and it's negative 7. Negative 7. Test statistic. If it's here, reject, or if it's out here, reject. So we're going to reject the null, which is consistent. That is consistent with our F test, our individual test of the slope coefficient, and our correlation coefficient. All three are giving us consistent information. Okay, that it looks like there's a relationship, ever so slight, but between the dependent and the independent variable. All righty, so again, 3 ways of testing that simple regression model for significance. Your individual t-test for the slope coefficient, your F calculated, which again is technically for multiple regression is at least 1, but when all you have is 1, it looks like we passed the F test, although I didn't give you the F critical value, but we barely passed the F test. And then the t-test for our correlation coefficient. Sam, I feel like I've given birth to an ANOVA table. Oh my goodness gracious me, man. Sam, we got questions. I'm like lost for words. What do you got, Sam?
Well, I think you've got them wowed with it because I have no questions for you.
Really? Oh my goodness. Well, I feel like I just jogged 20 miles. Come on, man. We're paying by the question. Okay, if there's no question, again, we appreciate your attendance tonight. We certainly want to reward you for that. We want to earn your business. So if you want, and you want a 25% off discount, here it is. So there's your code. In addition, yes, this is the other thing, folks. Yeah, Q Perkson at UWorld. Anybody want to earn a free CFA review course. You want to be our ambassador, whether it be at your firm or your university. So if you are currently getting an MBA program or an undergraduate program, if you're at a firm and you've got a cohort of 2, 3 other people studying for the exam, you could either get the course for free, or if you just have 1 or 2 other people, a significant discount. But my buddy Quinn handles the firms and the university relationships. So if you'd like to be an ambassador for UWorld, you've seen what we did. We have other videos online where I've done other topics. I can't even remember, financial statement analysis, fixed income, whatever we've done. So if you feel comfortable now, you've seen it, little test drive, and you feel comfortable and you want to be our ambassador, please email QPerkson, P-E-R-K-S-O-N, and we'd love to have you as part of the team, and you get a free review course if you've got a decent sized cohort that you're studying with, So that's that. Sam, what else, buddy? Do you have anything?
I just wanted to thank once again all of the folks who participated tonight and got to be the recipients and the beneficiaries of your good wisdom. So there will be a recording of this. The link will go out, let's say within a week. It may be a little bit sooner than that, but I just want to set expectations just in case they can't get the video edited for a few days. But you will get a link in your email, and you will have the ability to watch all of this again at your leisure. So with that, Pete, thanks so much. Thanks for your time, and a good night to everybody out there.
Thank you so much, everybody. We appreciate your attendance, and we will not let you down. No one in this industry is going to work harder to see you succeed. It's a joint effort, but you got to be willing and able to make that commitment. And if you could do that, we'll meet you halfway. So thank you so much, Sam. You're the best. Thank you. Thank you, Matt, if you're still on, and everybody behind the scenes. And I will see you guys in the next class.
Thank you all so much, and thanks for giving UWorld a chance here.
You got it. Bye-bye.